Let's look at random variables and expectation. Very big subject in probability and statistics. I want to approach it with an example without a lot of the terminology and then introduce the terminology after a while. We're playing a lottery game, and it's like a game called Keno, although I made up the probabilities just for this example. We write down 3 numbers, and then a computer comes up with 3 numbers, and we see how many matches we get. The more matches we get, the more money we win. We pay $5 to play, and if we get no matches, we just don't win anything, and we lose our $5, of course. If we get 1 match, we win $5, so we break even. If we get 2 matches, we win 40, and if we match all 3 numbers, we get $100. The probabilities, let's assume, are 3/4 of the time, roughly, you don't match at all. 1 out of 5 times, 20% of the time, you do 1 match. 5% of the time, you do 2 matches. And 1 out of 200 times, 0.5%, you win the big prize of $100. Okay? So the simplest thing we'd like to ask is it a good idea to play this game? First of all, I want to say that probability doesn't really say anything definite about whether it's a good idea to play this game just once. It really doesn't. But it does say something about, is this a good idea as a general rule in the long term? Is it a good idea to make it a habit to play this game? Is it a good idea to play it every day? So let's say, for example, let's say, to be definite, 1,000 times in a row. Let's say you play it 3 times a day for almost a year. Is that a good idea? There, the law of large numbers takes over and tells you that these probabilities are really going to be pretty close to a description of what's really going to happen when you do that. And we can get an idea of, are you going to lose money? Are you going to win? Or gain money overall? Or lose? Okay, so we're going to answer this question of, is this a good idea, in a very economist kind of way. Are you just going to win money or not? Now, some people might say, even if I lose money, it's entertaining. But let's discount that. Let's just see, how much will I gain or lose? Okay. Alrighty, so let's see. There's lots of different things that can happen, but we can kind of look at, for all of the different possibilities, we can look at the contribution to our winnings of the no match, 1 match, 2 match, and 3 match possibilities. Okay, so 745 times out of 1,000, we would expect, roughly, it's not precise, but it's pretty good, 745 times out of 1,000, we're going to win nothing. So let me just write that down. Let me put it in math mode to look prettier. 745 times of $0. Now that might seem silly, it's still $0, but it's going to be less silly in these cases. Okay, the 1 match, 200 times, math mode again, we're going to win $5. And again, these numbers aren't precise, but they're the best prediction we have. Okay, and they're pretty close to what's really going to happen. That's what the law of large numbers says, is that these are going to be pretty accurate. 50 times out of the 100, we're going to win $40. And that, and I forgot to do the multiplication here. That's $1,000. And then 50 times out of 4, that's $2,000. And let's see if this fits without going to let me just say contribution to wins. See if it can not take up so much room. 5 times out of 1,000 plays, you're only going to get the big jackpot 5 times, and that's going to be 5 math mode times $100 is $500. Okay, so what's our total winnings out of 100 plays? We just add these up. Okay, notice that what's going on here is that these are exactly 4 mutually exclusive outcomes that can happen, and so I don't have to worry about an overlap between these. It's either this or this or this or this, and that's going to be very important when we look at this in general. Something that can take just these values and they don't overlap. So the total winnings is just going to be the $0 math mode. $0 plus $1,000 plus $2,000 plus $500 is $3,500. Okay. All right. But the total paid was equal to $5,000. Okay. Okay, so losses are $1,500. All right, that's a huge loss, but of course we played 1,000 times. What we're more interested in is average, let's go back up here, the average winnings per game, per play, is 3,500 over 1,000, and that's $3.5. Put that in math mode to match it. Okay. And so average net loss per play was equal to $1.50. Okay. So if you play this game, on average you're going to pay the $5, you're going to win $3.5, $3.50, and so the net loss is $1.50. So the answer is, and this is true for almost all kind of lottery games, if you're actually trying to make money over the long term, it's a bad idea. You're going to lose $1,500 over this whole year, or in other words, each play is going to lose you $1.50 for these kinds of probabilities. Okay, so I hope that's a really, really relevant calculation, because it's the kind of calculation you really, really need to make in a lot of situations in your life if you have any kind of access to these kinds of probabilities. Lottery games and games of chance are actually better than almost anything else in life because they actually do give you the probabilities. In fact, state-sponsored lotteries are required to give you precise probabilities by law, and so you can actually calculate them. In a lot of cases, you have to kind of guess the probabilities. So the answer here was no, and the crucial number I want to highlight is this 350, the average winnings per play. This is what's called an expectation or an expectation value. Okay, so let me put in the notation here, the nomenclature, and explain what this is called. Okay, so what we've got is a situation, it's a standard probability situation where there's just 4 different outcomes. We've got these different probabilities. We can calculate the probability of this or that or this and that, all kinds of stuff. But it's special in that the what labels the different outcomes from each other are just numbers. It's winning 0 or winning 5 or winning 40 or winning 100. That's what I really cared about. I didn't really care about how it came to me. I cared about this number and all the different values you can take. Okay, so let's call that, just for the usual reasons, let's just call it X. Okay, and here's a subtlety though. So X is the prize won, and it's called a random variable. Okay, let me even put that in italics. And the idea of a random variable is pretty subtle. It's different from any kind of use of the word variable you've seen before. Usually a variable is something that secretly is a number that is in principle knowable. We just don't know it yet. Like when we're solving like 3x minus 6 equals 0. There really is a value for x. We just don't know it yet, and we just have to do some work to uncover it. Okay, that's I want to say it's different from the x in 3x minus 6 equals 0, because secretly that x is really 2. It's just we have to work to find it. A random variable is not something that has a definite value. It's a label for a random event or process or experiment that can give different numerical outcomes, like a lottery. Okay, so the random variable is simply the prize you may or may not win in a play of the lottery. Before you play the lottery, that doesn't have a value. Once you play the lottery once, then you say, okay, the random variable x in this case happened to have the value, let's say $40 if you got the 2 matches. And then we can look at the probability that the prize won was equal to, let's say, $40. This is how we say that. We translate it to saying the probability of the random variable x, which can have all these different outcomes, let me put that in math mode, okay, is equal to $40. Or we just state that as the probability of x equals 40. Okay, so this is the kind of symbol we're going to play a lot with from now on. The probability that some numerical outcome of some random process happens to be a certain numerical value. Okay? In this case, that probability is equal to 0.05. So I hope that this, when we stated it this way, that here's a possible prize you might win, here's the probability that you get that prize, that you didn't think this was something really new and different and weird. And all this weird statement says is just really what we were talking about here. The probability that when you play the lottery and you calculate the winnings, that those winnings are equal to a particular number, well, that's got to have some probability. But how likely is that situation? It's equal to 0.05 in this case. It's just saying the same information. Just a fancier way of thinking about it. It's a very crucial fancier way because we're going to do a lot with it. Okay. Here's a weird thing to do. Okay. I'd like to say, well, what's the probability that x can be all kinds of different values, not just 40? Okay, so we're going to do things like the probability that x is equal to little x, big X is equal to little x. Okay, what the heck does that mean? Why are we using the big X and the little x? The big X is, remember, the outcome of the experiment. It's a label. It's really standing for you better do the experiment and see what happens and calculate the prize winnings. Little x is the ordinary kind of variable. Okay, that's just a stand-in for I'm going to put a bunch of different numbers in here. Okay, so what we could do is we could say, let's evaluate the probability that the random variable x is equal to some number x for various values of little x, namely 0, 5, 40, and 100. That's exactly what these numbers are. Okay, so again, this looks pretty weird the first time you see it, but it really is just another way to say these really interesting numbers. If I'm going to look at the probability that the prize winnings, which is what x labels, is equal to various possible outcomes for x, and the reason we're using the same letter but just upper and lower cases is we're trying to say here's what actually comes from the experiment, here's a possible sample value that I'm interested in whether or not it happens. And evaluating that for these values of x is just exactly going to be these numbers. Okay, so what I'm trying to convince you of is that this is just kind of weird new notation for something that's actually a fairly natural thing to do once you have some grasp of probability. Okay, now what about this expectation idea? Okay, the expectation idea is something that's very important for a random variable, and it's exactly what we were doing when we were looking at this 350 number. Okay, the 350 number, I claim, is what's called the expectation. It's called E of x. I've got some random variable, some number that comes out of a random process, and I want to know on average what is the average value that x attains. Okay, and I can't just take 0 plus 5 plus 40 over 100 divided by 4. That would be a totally wrong average. Okay, that would be a rather large number, but it's totally wrong because I hardly ever get this 100. So it's basically a weighted average, weighted much more towards things that are more probable. Okay, and let's redo the calculation real quick. I went ahead to make things really concrete. I said let's do this 1,000 times, and so what we did is we looked at this number times 1,000 for how many wins you'd be likely to get in 1,000 tries, and this number times 1,000, and this number times 1,000, and this number times 1,000. But then notice what happened. After I added it all up, then I divided back by 1,000. Okay, so the simpler way to show the calculation is what I really did was 0.745, the probability that I get 0 times the value, plus the probability that I got $5 times the $5, plus the probability that I got $40 times the $40, plus the probability that I got $100 times the $100. That calculation just gets me directly to the $3.50, 3.5. This is a great example of the expectation value of a random variable. And you always can think about it in terms of like winnings for a lottery. You've got various different values that the random variable can attain, and then I just multiply those by the probabilities that it could have. Okay, so notice how that would work if in the symbols. Oops, didn't mean to do that. How that would work with the symbols is we're taking the probability that x equals 0 times 0, plus the probability that x equals 5, the winnings equal 5, times 5, plus the probability that x equals 40 times 40, oops, and I lost my cursor, plus the probability that x equals 100 times 100. And that's really not, it's really getting confused as to what it should do with that thing. Let's not put that in the same display, shall we? Okay. And that's what came up with the 350. So this is a general recipe for expectation values. Look at all the possible values that your random variable can attain, like all the different winnings, and just multiply them by the corresponding probabilities, add up. And you get what's called the expectation value, or the expected value of your variable. Okay? So yeah, this is called the expected value. There's a lot of different slight variations on how to do it. And it's really just, on average, how much do you win? Okay.